Good evening, everyone. We are in the week 3 problem solving session of the NPTEL course Control and Tuning Methods in 6-mode power converters. And week 3 is about fixed frequency modulation techniques. I am Teja Golla, a PhD scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes.
Hello.
Yes.
Yeah. So in week 3, sir has discussed about practical voltage source and various modulation techniques, which we might have already covered in the last week. But again, we'll discuss if you have any queries regarding that. So to start with, the first problem is about practical voltage source, and it says draw the circuit diagram of a practical voltage source and its corresponding MATLAB model. So can anyone tell me what is a practical voltage source and how is it different from an ideal voltage source?
The voltage source having a resistance, there is resistance.
Yes, so resistance is something that we consider, but it will also have parasitic inductance as well as parasitic capacitance. So let me write the or draw the diagram. So first I'll start with an ideal voltage source, and I hope you are also practicing the MATLAB simulation. Are you doing MATLAB simulation?
They're trying.
Okay. So today I have also added a MATLAB simulation of this practical voltage source, so that if you have any queries, you can ask me, and also it would probably, I was under the impression that it will motivate you to do MATLAB. So I thought I'll add one MATLAB model. Probably if it is engaging and if you are getting benefited, I'll add few MATLAB models in the upcoming sessions also. So ideal voltage source will look something like this. Here I can connect a load, resistor or anything. So this is my input voltage and it is say drawing some current I0. Now, no matter how much I draw, so if I draw V versus I, no matter how much current I draw, this voltage will remain V in, which means even if I'm drawing 1 ampere, the supply voltage will be V in. Even if I'm drawing 2 amperes, the supply voltage will be V in. Even if I'm drawing 100 amperes, the supply voltage will be V in only. So it's an ideal voltage source. So because of this reason, it is called ideal, because in practical case, it will not be V in, it will be slightly lesser than V in. So why do we consider ideal voltage source? Just for our simplicity, because the voltage sources or the voltage supplies that we use will have huge capacitance at the output. So it will be closer to an ideal voltage source, although there will be few parasitic. So we are a good voltage source will be that voltage source which is as close to the ideal voltage source. So that's why we also consider Vin as an ideal voltage source just for the simplicity. But in practical case, it will slightly deviate, not that much. But we'll see if there is any parasitic, how is it going to affect the input voltage. So because of this reason, it is also said that it is having infinite bandwidth. Means if you see, even with respect to frequency, it is independent of anything. So if you draw the input to output Bode plot also, it is independent of frequency. So that's why it is having infinite bandwidth. But if it had any parasitic inductance or capacitance, then it will be a function of frequency. So then it will have finite bandwidth. So now coming to practical voltage source. So as you said, there will be a parasitic resistance in series. So what happens if there is a resistance? Then if we increase the current, then the voltage that is seen over these two terminals will be lesser because of the drop across the resistance. So in that case, the actual voltage that we see versus the voltage that is being supplied by the source will be different because of the parasitic loss. But it is not just a resistance, it will also have parasitic inductance. So the circuit will look something like this: parasitic resistance, then there is some inductance, and output side also there will be finite capacitance, and this is my input voltage, and this is my actual terminal. So these are the two terminals where I can connect a load, whether it be resistance or anything. So now my input I am calling Vin, this one I am calling R1, this I am calling L, this I am calling R2, this I am calling C. So now this is my I naught, the load that I am giving it to, the current that I am giving to load. And let us, now it's a second order system, right? Why it is a second order system? Anyone?
You have three storage elements, two storage elements.
Two storage elements, right? Yes, yes. So you're correct. We have two storage elements, one being the inductor, one being the capacitor. So when we have two storage elements, yeah, Jinsi Joy, both L and C, yeah, you are correct. So when we have inductor, we consider state variable as inductor current as state variable. For capacitance, we will consider capacitor voltage as state variable. So let us consider this one as IL, and this current as IC, this voltage as VC. So what are my state variables? My state variables are IL and VC. So why is it important to identify the state variables? Because this will help us to develop the MATLAB model, which we are going to do now. So far is it clear? Whatever we have discussed, the difference between the ideal voltage source as well as practical voltage source.
Yes, sir.
Yes,
Okay,
yes,
okay.
sir.
Yes. And is my audio clear, or are you facing any noise, fan noise or something like
It's good, sir. No issues.
that? Okay. So now we have to make a MATLAB model using these variables as well as the equations. So any simulation or any Simulink, any simulation is a mathematical equation, right? So the simulation does not know whether we are connecting a buck converter, or it will not know whether we are connecting a practical voltage source. So it sees it as a mathematical equation, and it starts to solve the equation using whatever solvers. Like there are different solvers, which I will show once I move to Simulink. But you can say it uses Newton-Raphson method. So it's a equation, and it will try to solve. So we have to implement the given circuit using the blocks that are available in the Simulink model, and based on the blocks that we have used, it will try to solve the mathematical equation. So how are we going to implement this using Simulink? So we will be using certain blocks like gains, constant, as well as 1/s blocks. So using these blocks, we have to represent this circuit in the Simulink. So we will be using 1/s block, which is like an integrator. So how are we going to write everything in terms of 1/s? So let us start with inductor. So voltage across inductor, what is it? And let me call this output voltage as V0. So this is V0. So now VL is nothing but V in minus IL into R1 minus V0. Agree? So if you face any difficulty at any equation, please let me know, because I am considering one simple example. I will not be able to cover all the examples of all the converters. But if you are clear with the concept, even for this example, you should be able to extend it for other converters as well. And I know VL is nothing but L into DIL by dt. Now I will write DIL by dt is equals to 1 by L into V in minus IL into R1 minus V0. So now let me try to represent this in terms of blocks, MATLAB blocks. So how do I represent? So Vin is a constant. So I will use Vin as a constant, then followed by summer. So Vin is getting added, then IL into R1 is getting subtracted, then V0 is also getting subtracted. Now this will result in some value that I have to multiply by a gain of 1 by L. So far, is it clear?
Yes, sir.
Hello. Yeah.
Yes.
Yeah. So now where are we going to use the integrator block? So the output of this is nothing but DIL1 by dt. So if I pass this through
Your
an
integrator.
integrator, yes, you're right, I'll get IL. So that is what exactly I'm going to do now. I'll pass this through, sorry for the bad drawing, 1 by S, then my output is IL. Now if you see, this IL over here and then this IL over R1 are dependent on each other. So I can feed back this IL. So I need IL into R1, right? So what I'm going to do, I need IL into R1. So this is my IL. I will use another gain R1 and then I'll feed it back. So this is for the inductor. So based on the inductor equation and V0 expression, I am getting this block diagram where my input is Vin, V0 and ILR1 is coming from the loop and output is my IL. So this is for the inductor. So far what we have done is for the inductor. Now we have to do the same thing for the capacitor also. So far is it clear?
Yes, yes.
So if you have any doubts, please stop me, else I'll move ahead.
Clear, sir. No issues.
Okay. So now let us go to the capacitor. So what I do I know about capacitor? I know for inductor V equal to LdI by dt. For capacitor, I know I equal to C dVc by dt. So I will write everything in terms of capacitor current. So from the KCL, I can write IL is equals to IC plus I0. So IL is equals to IC plus I0. From this, I will separate IC. IC is nothing but IL minus I0. And what is I0? V0 by R. So IL minus V0 by R. So this is one expression that I will be getting. So IC is nothing but IL minus V0 by R. So if we have to represent this using MATLAB, I can write my input is IL. Then I'll again have a summer block. From there, I am subtracting V0 by R current and my output is IC. So basically, I can do this. I'll connect this IL from here to here. So I am getting IC from IL as well as V0 by R. Does this end the problem? No. My final output of the entire block is V0, right? So my final output should be V0. It cannot be IC because my input is Vin. Overall block diagram output should be V0 because I am feeding V0. Sorry, I am feeding V0 to the subsequent circuits. So overall output of the block diagram should be V0. So we are only halfway there. Now we have to write the expression for the output voltage. So this is my output voltage. So how do I know what is my output voltage? So this is simple. From here you know that V0 is nothing but VC plus IC into R2. So sorry, V0 is equals to VC plus IC into R2. So IC is something we have already calculated. Yes, right? IC is something we have already calculated. But how do I know VC? So for calculating VC, I know that IC is equals to C dVc by dt. From this I can say IC into 1 by C is nothing but dVc by dt. Now I will pass this through an integrator. So say my input is IC, then I will pass it through a gain which is 1 by C. Now I will get dVc by dt. Now I will pass this through an integrator to get Vc. Is this clear?
Yes.
So now how do I use this Vc to get V0? So I'll just draw this here so that I can take advantage of the space. So now I am getting Vc. So now I am getting Vc. This Vc has to be added to IC into R2. So this is my IC and now this is my R2. Both are adding and then I will get V0. So from where is this IC coming? This IC is coming from the previous block that we have over here. So this IC is coming from this previous block and this IL is coming from this previous block. So let us draw the overall diagram. So what I will do is I will use this diagrams only. So far the concept is clear, right? We are designing individually and then
Yes.
we'll combine.
So
And
same
then
holds good for a buck or a boost, any converter,
yeah,
right?
for any converter it's the same.
So we have to write the expressions for inductor and capacitor.
Yes.
How many
And
state
in the
variables are there? For all the state variables, you have to write the equation.
yes, exactly. And only change in the case of switching converter is in switching converter there are two configurations. When switch is on, when switch is off. So you will get a switch in between. When Q is on, these are the connections. When Q is off, these are the connections.
Okay, fine.
So from IL, I'll write IL plus minus V0 by R IC. So from IL, I'll pass this through a block, plus here, minus here, V0 by R, then I'll get IC. This is the block, that intermediate block that we had over here, just to calculate IC. And from now, IC, I will draw this entire block. So from IC, I'll draw the same thing. We have 1 by C, then we have 1 by S, then we have output is V0, then plus an R2. So from here I will have R2, then I'll add it over here. This is plus. So this is the overall block diagram. But is the block diagram done? No, because if you see here we are using V0, right? Similarly, here V0 is there, here V0 by R is there. But how are we going to get this V0? So this is coming from the output voltage. So this V0 as well as this V0 should come from this guy V0. So we have to feed it back. So let me erase this V0, this V0 by R. So one is current, one is voltage. So what I will do, I will put a gain of 1 by R and then feed the current over here. And then I will take V0 and then I will feed the V0 over here. So this is V0 by R, this is V0. So first I have written the variables in terms of V0, IC, IL. Then I have slowly combined the overall to get the overall block diagram. And then I have replaced. If you see here, I have written it first in terms of ILR1. But once I got IL, I have generated this ILR1 from IL. And then there is a feedback here. Similarly, initially I have written this in terms of V0 by R. But once I got V0, I have generated V0 by R as a feedback. Similarly here also. Whereas here I needed a feed forward because IC is getting added to VC to generate V0. So this is my IC and this is my VC. Yeah. So in this way we are getting the overall block diagram. So now once we make this in the MATLAB, then we can run it and see. This is my actual ideal voltage source. So this is the ideal voltage source that I actually want, and this is the output of the practical voltage source. Practical voltage source. So based on this, we'll know how much is the deviation and how is it going to act different from the ideal voltage source. So far, is it clear?
Yes, sir.
Okay.
Yes, sir.
So if you have any doubts, you can ask, else I'll quickly show this. Okay. So now say instead of one resistor, I have two resistors. Say, oh, sorry. Say instead of, before going to Simulink, let us say there is two types of resistors. So at the output V0, so at the output V0, I have R1, then I have R2, then I have a switch, complementary switch. Okay, so this is my plus minus V0. Here I am giving Q, here I am in Q bar. So if Q is on, R1 is connected. If Q bar is on, then R2 is being connected. So instead of using single resistance, I'll be using two such resistors. So in that case, how are we going to do? So entire circuit will remain the same, only this part will change. So how this part is going to change? So I will have a switch. It will take the input Q, and then either it will connect this to the output or it will connect this to the output, right? So I'll feed, like I'll use the same one so that it will not be issue. Yeah. So here I have 1 by R1. Here I'll have 1 by R2, and this is the output that is going. So both input is V0. So here if Q is equals to 1, then this will be V0 by R1. If Q is equals to 0, then this will be V0 by R2. So this is the switch that is available in the MATLAB model. So which is what exactly I have done over here. I don't know whether both can be seen. So now you can correlate, right? Like you can just check. So this is my Vin. Let us for the time being remove this, and then you check V1, then L1, 1 by L, then 1 by S, then I1 is being calculated, which is getting feedback as R1. Then there is another summer from which V0 by R is being subtracted. Then we have 1 by C, then 1 by S to get VC. Then R2 into I2 IC is getting added to give V0. Now V0 is being fed back to 1 by R1 as well as 1 by R2, and there is a switch. So if this is on, then 1 by R1 will go, else 1 by R2 will go. So this is my 1 by R1, this is my 1 by R2. I think someone is drawing on the screen, kindly please erase. So this is my V0, and this is my outer loop V0. So this is my actual voltage source, this is my practical voltage source. So now what are we doing? We are checking both this actual one and the practical one, ideal one as well as the practical one. And then I am sending this data back to the workspace. So that's why I have used this block. I think sir also has explained this is two workspace block. So I'm not going to explain each and every like how to make all these things, because that is already taught by sir. I have just showed how to get this MATLAB model. So far is it clear?
Sir, actually you have two resistance, right, sir?
Yes. So this is my Q. If Q is greater than 0, 1 by R1 will be connected. If Q is less than 0, 1 by R2 will be connected. So either of the switch will be connected, not both.
So what is the name of this block? Sir, change over switcher.
This one, this is switch. So you double click anywhere and write switch. So this is the switch.
Okay,
I have just
switcher.
inverted. And then
Okay.
one block is the gain block that I have used. The other one is the integrator.
Integrator.
And this is the pulse generator. So you can double click anywhere and generate pulse generator. Inside you have to give how much is the frequency, everything. So if you go,
Why we are comparing this V in and V naught, sir?
so I can see what is the expected input voltage and what is the voltage that I am getting finally.
Fine, fine. Because of these resistance and inductances, we are not going to get the actual.
Yes, yes.
We'll be having a drop.
Yes. So that drop is what I am planning to see, and then let us see what happens.
Okay.
So why am I giving 1 by R1, 1 by R2? I want to see if the load is changing, whether output voltage is changing or not as a function of load.
Actually, it
Is
should
that
not
clear?
change.
Yes.
Sorry.
You proceed, ma'am.
Hello.
Sir, I have a doubt.
Yeah.
Sir, say all these things we can do with the Simulink itself. No, sir. Why should we go for that workspace?
Yeah, yeah. So
Especially.
I'll also show that. Yeah, good question. Let me run it. I'll show you why to go to workspace, right?
Okay.
So this is my workspace. So I'll come back. Once I plot this, I'll explain. So this is CLC, close all, clear all. So this is basically CLC is to clear the command window. Clear all will clear the workspace, what all values. So this will be cleared, and then CLC will clear this command window. So whatever parameters I have used, I have defined over here, like input voltage R1, inductance R2, capacitance, and the load resistance R1 as well as R2. Then I have given initial conditions. This is one important point I would like to add. Where is this initial condition coming? So for the integrator, you have to give the initial condition, because from where does it start? Like this is a mathematical equation, right? That the simulation is solving, solver is solving. So it needs an initial condition. From where do you want to initiate the solving process? If you are starting from a value closer to the solution, then it will reach faster. If it is far away, then it will take time. So it is just to start the simulation as close as possible to the solution. Even if you start from far, then it will take some time to go there, but you are free to choose any value. I have chosen capacitor voltage as V input so that it will immediately reach the steady state. I don't want to see the transient. And then Simulink time I have given tsim, which I have mentioned over here, stop time, which is tsim. So I am giving this tsim, which I have defined over here, and then I am opening the Simulink. Open will open, I don't have to open. Sim will simulate it. So once it simulates, then if I have to see the data, I will double click on this and then I will see here. But what I can do is I can take the data back to the command window or this my workspace. Why? Because here the data is being plotted, but what if I have to process the data? Say I want to plot it in a different way. Then what I do, I am saving in a data variable called data, so it saves time, and then it has two columns. One column is coming from the input, which is V, and the other column it is coming from this one, which is V output. Then I am using the command, figure command, plotting the time versus input, plotting time versus output. Once I'll run, I'll show you what are the input and output. Yeah. So this is my input and output. If you see, input is always constant 12 volt, but output is varying and there are spikes because of the inductance. Because of the L and C values, it is acting like a second order filter and it is having these spikes. And as you can see, if the load current is more, the dip in the value is more. If the resistance is lesser, here if you see, one is 1 and one is 0.1. So I am drawing certain amount of current, and based on the current, the drop has changed. Now in order to understand this, I can change the value. Say if I make R2 to be 2 instead of 0.1, then the drop should not be more. So that I can check. So drop will not be significant. As you can see, the value is coming very close, 11.985. Previously it was too much, now it has come as close as 12. So if I'm drawing more current, then the drop will be more because of the resistive drop. So these spikes are because of the inductance as well as capacitance. So now I can vary the values here. Say instead of 10, if I put 100 microfarad, then I'll see how the how it is functioning, whether the damping will improve or not. So damping will improve. Why? Because damping is what? R by 2 into square root of C by L, right? If I improve my capacitance, then the damping will improve. So previously it was very much underdamped. Now it is slightly underdamped, and the spikes have significantly reduced. So if I have the control over inductance, I can make the inductance much smaller. So inductance is the reason it is causing spikes. So if I reduce the inductance, then the spike will be gone. As you can see, the spikes are gone because the damping has been reduced. But parasitic is something that we don't have any control over it. So instead of changing, we cannot reduce the inductance, right? That is by default it is there. It is coming from the parasitic of the source. So all I can do is increase capacitance. So I can increase the capacitance. So this capacitance, which initially was 10, I have made it 100. And coming to your question, if I can take this data over here, I can use my own colors and then I can plot. I'll show you. Say this is K. So one is red, or okay, output I'm keeping. So R means red color, B means blue color. Okay. Yeah. So one is blue, one is red. For which condition? For a condition of L is 0.1, C is 100. Say now I make C to be 400. Now I want to see the current result versus the previous result. So what I will do, I will comment this close all. Close all will close the existing plot that is open. So now I am making that my plot will be open. And then I want to compare the existing one with the new one. So I will put dash. Dash means it will be dash line instead of solid line. So I will make it black color, and then on the red I will put blue color or green color, dash dash green. So I have changed the capacitance value, and I wanted to see how my current output will change with respect to the existing one. Did I close it? Acha. Because I have not given the figure name, it has opened a different figure. So let us do one thing. Let us give the figure number, figure name. So I will give figure 1, and then initially this was red. Sorry, initially this was blue, and this was red. Okay, and capacitance was 100. Okay, now I will increase the capacitance to 400, and then I have changed. So this is dash dash black, and this is dash dash blue. So I'll run it again. So now it is plotting on the same, and I can see both what is the impact of the capacitance. If I'm increasing the capacitance, it is increasing the damping, and I can see the damping has improved from underdamped to overdamped. So this is the advantage to take the data back to the workspace, because we can save it and then plot it multiple times. Whereas in the case of Simulink, you don't have that option because the data will keep on updating, right? But in the case of workspace, I can save it in one variable and I can make a comparison, or I can change offset if I want to multiply by gain. So all this data processing we can do only if we store it in a variable. So that is the advantage to take it back. Here we have the full flexibility. And when you are posting, or I mean saving this figure as PNG to keep it in your report or any paper, you have to export it, right? So you can do the same. You can save it as an image. So you can save it as an F figure or PNG or JPG, which you can keep it wherever you want. So you have this flexibility. So that's why we take it to workspace. And I have written the code in such a way that I don't have to open anything. One single click, it will only open the Simulink, it will only simulate, and it will only plot the data. So it will make my life simpler. So that's why I have done this. If you want, I can share this MATLAB file as well, and I'll upload to the Google Drive. So that is the overall idea of practical voltage source, and I thought I will show you the MATLAB model development also. So is that clear?
Yes, sir.
Okay. Any doubts if you have,
Yes,
you can
sir.
ask. Okay.
Even we can plot voltage versus current also, sir.
Yes,
So,
yeah, that is, yeah, very good. So I can plot IV graph as well. So I have the full
that is
flexibility.
not possible in Simulink, sir.
Yeah, maybe possible. There are options, but again, you have to change the option and check. Whereas here you have the full flexibility. Instead of time, I'll put I, then I can plot IV. So that is also good, good thinking. You can also plot IV plot. So I can see how my voltage is changing with respect to current. Yeah. We can do it very well. Yeah. So there is less than a minute. This meeting will end, and once it ends, kindly join back. So before that, peak and valley current mode control, draw the timing diagrams for peak and valley current mode control and show their corresponding circuit implementation using comparator and SR flip-flops. So this is something we have already discussed in the previous week. So let me pull that week 2 notes. Yeah, so this is the one I was discussing. Peak and valley current mode. You remember this, right?
Yes, sir.
If this meeting ends, kindly join back. I hope you can see my screen.
Yes, sir.
Yeah. So I'll not explain what I have explained in the last week, just to save time so that we can spend it on some other concept. So this is the peak and valley current mode control that we have discussed previously in week 2, where we have mentioned again, there are two types of nomenclature. When we say edge, we are discussing about the current. So trailing edge means current is trailing, means current is below the current reference, and current reference is at the peak. So it's peak current mode control or trailing edge control. One is leading edge, sorry, trailing edge modulation. One is leading edge modulation, which is valley current mode control. So I have asked to draw the timing diagrams, and once timing diagrams are drawn, I'm asking how to implement using comparators as well as SR flip-flops. So it is also easy. So this is set pulse generation. So whenever this hits, then set pulse is generated, and whenever this hits, reset, sorry, my bad. Whenever this is hit, reset pulse is generated because inductor current is falling. Whenever this is hit, set pulse is generated because after that it is starting to rise. So first we have to generate the reset pulse, which is comparison of IL and I reference. So plus and minus. Be careful with the plus and minus. Probably I'll use a different color, so you'll take a note of it. So this is plus, this is minus. So whenever IL is crossing I reference, it will be reset pulse. So this is my reset pulse. Then I have RS flip-flop or SR flip-flop, and set pulse is coming from a fixed frequency because it's a fixed frequency operation. So it is fixed frequency pulse is setting, and then reset is coming from the loop. So whenever IL is going above I reference, then this will generate reset pulse, and then the output will become 0. So this is my Q. So in this way, my pulse is being generated using peak current mode control. In the case of valley current mode control, set pulse is being generated from the comparator output. So it is slightly different. So notice the changes. Here IL will be opposite. Whenever IL is going down, so this will be I reference and this will be IL because it is valley current mode control. So that's why the change. Whenever IL is going below I reference, then set pulse will be generated. So this is set pulse. This is set pulse, and then reset pulse is coming from the switching frequency. So what is the modulation technique for variable frequency? That I think will be discussed in week 4. So we can see how it is being generated in the upcoming week. So this is how we implement current mode control using a comparator as well as flip-flop. So since my MATLAB is open, let me show you. There is a flip-flop. So you double click anywhere, you write flip-flop, D flip-flop, JK flip-flop, ours is SR flip-flop. So set pulse is a fixed frequency, and the initial condition you can put 0 or 1. So set pulse will be coming from comparator in the case of valley current mode control. In the case of peak current mode control, it is opposite. And then there is, for comparator, there is a name, I forgot. There is one name for comparator. It is not comparator or something. There is one name. Let us check in the library browser. Relational operator. So comparator is not called as comparator. Instead of that, it has a different name. So the name is different. So that's why I keep forgetting. It's a relational operator. Here you have to see the up one means the input 1 is less than or equal to input 2. So you have to be very careful when you are using it as a plus minus or minus plus. So here input 1 is less than or equal to input 2. I can also use input A1 is greater than or equal to input 2. So just be careful. Try to play with the block initially before making the closed loop. So these are the blocks that you will be needing to implement the current mode control. So is that clear? Problem 2.
Yes, sir.
Okay. Any questions, others?
Yes, sir. Please, understandable, sir. No issues.
Okay. So now coming to a different problem, which is input voltage feed forward. So what are we doing in input voltage feed forward? So the ramp voltage that we generate usually is from 0 to 1. Instead of that, we are multiplying with input voltage as well as some gain KFF, so that the ramp voltage, which was initially 0 to 1, will now not be 0 to 1. Yeah. So now instead of 0 to 1, it will go from 0 to KFF into Vin. So what is the benefit of this? So let us see. And it is being compared with VM. So from this, what will be the expression for duty ratio, anyone?
Duty ratio of
For output of this. So if I'm generating the output of this, what will be the duty ratio value for this set of voltages? So this is the duty ratio, right?
Zero to V in.
Yeah. So if I'm comparing VM, if I'm comparing VM and the peak voltage is KFF Vin, what will be the duty ratio? Are you getting the point, or should I reframe my question?
For 0 to V in, we'll be getting the output as
Okay. I
V in.
think I'll reframe. So say this is my sawtooth, and I am comparing. Say this is my 1 volt, and then I am comparing 0.1 volt. So what will be the duty ratio? Output duty ratio? The output of this. So I am comparing with this, right? And this is my Q, right? This is my Q.
10%, right?
10%, right? Or I would say 0.1 in if I'm saying in decimal value. Say instead of 1 volt, I'm using 2 volt here, and I'm using 1 volt here. What is the duty ratio?
50%.
50%. Very good. So now instead of 1 volt, I am using VM. What is the duty ratio?
V in by 2.
VM by 2. Very good. So instead of 2 volt, now I'll use KFF into Vin. What is the duty ratio?
1 by KF.
V in. So this is V in,
For VM.
not VM.
Okay. Vm by KFF into Vin.
Very good. Vm by KFF into Vn. So we are getting a duty ratio which is dependent on Vm as well as input voltage. So let us see how is it going to benefit us. So that's why I have asked these three sub questions. First question says, which of the following converters has an output voltage independent of input voltage? So for a buck converter, what is the output voltage and input voltage relation? V0 is equals to
dVn.
dVn. So now if we substitute this duty ratio, what is V0?
Vn will get cancelled out, it seems.
Yes. So very good. It will be Vm by KFF, right?
Vm by KFF.
So in the case of buck
So it
converter,
is independent.
yes, very good. In the case of buck converter, if we are using input voltage feed forward, the output voltage will be independent of Vn. So we are getting a benefit because say in the first example you have seen that input voltage is dependent on the load current. It is not 12 volt. It is swinging between 11.9 and say 12 volt. I don't want the output to be affected because of the supply. Then I'll give input voltage feed forward and my output voltage is independent of input voltage. So here I'm getting this benefit. So sometimes input voltage feed forward will help, but whether it will help always, that we can see by checking the buck converter as well, boost converter as well as buck boost converter. So for boost converter, what is the output voltage expression in terms of input voltage and duty ratio?
V0 by Vn equal to 1 by 1 minus G.
Yes, 1 by 1 minus D. So now let us see what is my output expression. So V0 is nothing but V in by 1 minus Km by KFF into Vn.
Vm by KFF into V.
Sorry, yeah. Vm by KFF into Vn. So now it is not a function of Vn is not getting cancelled, right?
Yes.
Yeah. So here I am not getting any benefit dependent on Vn. Still dependent on Vn.
Yes.
Now let us do the same for buck boost converter. What is V0 express non-inverting? So minus sign will not be there. So what is the relation
D by
for
1 minus.
D by 1 minus D into Vn? Good. So let us see. V0 is Vm by KFF Vin into Vin by 1 minus Vm by KFF Vin. Yeah. So Vin will get cancelled. It will be Vm by KFF by 1 minus Vm by KFF into Vin. So if I take Vm by KFF common on the numerator and denominator, I'll get 1 by KFF by Vm minus 1 by Vn. So it is still dependent on Vn. So this is still dependent on Vin. So why in the case of buck converter it is independent, but in the case of other converters it is dependent? Because if you see the expression of duty ratio, we are getting Vin in the denominator, and for buck converter it is D into Vin. So Vin will get cancelled if Vin is in the denominator for duty ratio. Whereas in the case of boost converter, 1 minus D should be a function of Vin, so that Vin will get cancelled. So D should not be a function of Vin. 1 minus D should be a function of Vin. So accordingly, I have to come up with a logic so that D will be not a function of Vin. Instead of 1 minus D will be a function of Vin. But in the case of buck boost, non-inverting buck boost, neither D nor 1 minus D, but D by 1 minus D should be a function of 1 by Vin. So Vin will get cancelled. So based on the objective or the aim that we want to reach or accomplish, accordingly we can solve it back. We can synthesize the problem backwards. In the case of buck converter, D should be proportional to 1 by Vin, which we can be done directly by implementing this. But for boost converter and non-inverting boost converter, it will be slightly difficult. And since sir has not discussed, let us not discuss that, but you can see the benefit, right? Like and you should also understand why certain converters has that benefit and certain converters don't. Because of the obvious reason, V in get cancelled. In the other case, it is not getting cancelled. Why? Because 1 minus d should be proportional to V in. Similarly, here d by 1 minus d should be proportional to 1 by V in. And that's why it is independent. It's not independent of V in, and it is dependent on of V in both B as well as C. Is that clear?
Yes, sir.
Yes.
So moving to the last part of the discussion. So this problem, I thought I'll explain in terms of practical application. So before we solve this problem, I'll quickly give background of this. So have you gone through sir's lectures? Do you know what is PoL converter? Do you know what is IBC converter?
No, Teja, we didn't go through that. Can we give a quick glimpse about this?
Yeah. Anyway, I was planning. So my research topic is also little bit covered. So I thought I could give you little bit background study of this. So you know data centers, right? Data center?
Yes, sir.
Yeah. So in data center, you will see these type of racks, multiple racks in the entire data center, and each rack is either you can plug in or you can remove it. So this is where the processing happens. Like even if you use ChatGPT or Gemini, you write a prompt and then it is processed somewhere, right? It is not processed in your laptop. It is processed in cloud. So where is this cloud? So the cloud is in the data center. So whatever ChatGPT commands or Claude or Gemini that you use, the prompts that you give, it has to process it somewhere, right? So it processes it in the data center. So now the data center has several such vertical cupboard type of things, and in each such cupboard we'll have multiple racks. So this is one you can say rack, not exactly, but something similar. So I thought this will be easier to understand than the actual rack. So the actual rack will have a CPU unit at the center or GPU, whatever they are using, and then this will do the processing, something similar to your laptop. Say laptop has Intel processor or AMD processor, mobile phone has Snapdragon processor, or iPhone has Bionic A18 Bionic chip or something. So now it will process, right? So it has to process a 1 mega instructions, 1 million instructions per second or something it is processing. But who provides the power to this processor? So there is a power converter sitting right in front of the processor. Here, this is the converter that is sitting. So this is called PoL converter. PoL, which is point of load converter. PoL converter. So what it does is it will give the necessary power in terms of voltage as well as current to the CPU. So typically multi-phase converters, multi-phase buck converters are used. Again, I'm not going into these details. I'm just giving you the overall surface level idea. So multi-phase converters are being used just before this processor. But there is an architecture that people follow in all the data center. So for each of this rack, the input is 48 volt. So the input to this rack, input is around 48. Matlab, it is called 48 volt bus and it is unregulated. So that's why it can vary from 40 to 60 volt. So which is shown over here, 40 to 60. Now the CPU that we use or the GPU that we use requires a voltage around 0.8 volt to say 1.8 volt, very less voltage, and it consumes hundreds of ampere. And now with this AI going on, it will in the future it will go to few thousands of amperes at this low voltage. Now I have to step down a DC voltage to another DC voltage. I can use a buck converter. But if I say use a buck converter from 48 volt to 1 volt, the duty ratio is 1 by 48, which is very less. So I can't use a single buck converter. So that's why what people do is this 48 volt bus will be converted to a 12 volt bus, and then I have my CPU over here. So 48 volt is converted to 12 volt. using a converter called intermediate bus converter. So IBC, full form I have written in this here. So IBC is intermediate bus converter, just to reduce the 48 volt to 12 volt. And here we will use the PoL converter so that it will supply the power to CPU. So what is the requirement or the specification of the IBC? So IBC's main objective is to step down 48 volt to 12 volt. So it is unregulated. So the 12 volt also can range, can vary from around 6 volts to 16 volt. So IBC has to be very high power dense, so that we are just stepping down to 12 volt. Why we are stepping down? Because then the duty ratio will be 1/12 instead of 1/48. And the requirement or the requirement of the PoL is to supply whatever power CPU is asking for. And what are that requirement? Requirement is the transient performance. Say I have turned on the laptop and I have kept it in the idle mode. So now the CPU is not consuming any power. Now what I will do, I'll run a MATLAB. So now it immediately starts power. So it immediately needs that power to run this MATLAB. So who is giving that power? That power is giving by this PoL. So the faster the PoL supplies the power to CPU, the faster the CPU can start working on it, and then MATLAB will run quickly. So overall, whatever this AI thing, everything is going, it is dependent upon this PoL, how much fast it can give the power to the CPU so that CPU can process. So my work is related on this PoL, multi-phase buck converter, and I'm working on the control of the converter, how to control it so that the transient response will be faster. So here I have considered one NVIDIA H100 GPU. So this is a product. So this is a product of NVIDIA H100 GPU. You can also search online. So the center part is this. This is the GPU. So now you can see the input is coming 48 volt, and 48 volt is being converted to 12 volt. So this is the IBC, intermediate bus converter. So it is just to convert 48 volt to 12 volt. So it should be high power density. So that's why it is small. And the rest of the board is 12 volt to 0.8 volt multiphase buck converters, only to supply all the current that it needs. So if the current requirement is 100 amperes, maybe I'll need 4 such buck converters. If my current requirement is 1000 amperes, I will need 40 such buck converters. So all the entire board is full of buck converters because of the requirement of this GPU. In the future, this GPU requirement is going even higher because of this AI. In that case, how are we going to control these converters? How to implement this? Because the area is also increasing, right? So research is going on in multiple directions. Mine is system level. Research is also going on in integrated level, where converter will be within an IC. Again, that is beyond the scope of this course. So this discussion is to give an overall idea of this 48 volt bus architecture. And since there are two such stages, one considering of IBC, other consisting of PoL, this is also called as two-stage architecture. This is called as two-stage because stage 1 has IBC and stage 2 has PoL. If you see, IBC's task is to just step down 48 volt to 12 volt. So here the requirement is not huge, whereas PoL is sitting right in front of CPU. So the moment CPU starts computing something, PoL has to give the power. So PoL has to work at a higher bandwidth than IBC because it is sitting in front of CPU. IBC can be little bit slower, it should be fine. But PoL has to be little bit, not little bit, much faster than IBC so that it is directly supplying power to CPU. So here the requirements are higher. So that's why people operate PoL at a higher frequency. So here switching frequency should be higher, bandwidth should also be higher because it has to respond immediately to whatever CPU is demanding. So that's why the second stage or the last stage, I would say, will operate at a higher switching frequency because it is the one to immediately respond to what CPU or GPU is demanding, and also the bandwidth of the PoL should be faster. Since IBC is sitting before PoL, PoL is what is demanding the power from IBC. So on the CPU side, at the edge, the demand is higher. So this will be faster. Coming slowly back, the demand or the requirement will become little bit lesser. So IBC can work at a lesser bandwidth compared to that of PoL, and also the frequency can be lesser because bandwidth is lesser. If I'm operating at higher frequency, bandwidth will be higher, so PoL will be operated at higher switching frequency. So this is a brief overview that I wanted to give regarding what is happening, and since it is related to AI also, I have just given some brief overview, and that will
Nice.
also solve this problem. Any queries or anything you would like to ask regarding this?
Yeah, it's nice. Thank you
It's
for
nice,
Yeah, yeah.
very informative for us.
Yes, yes, yes. I also thought like this is very interesting for me, not just because it's my research topic, but I somehow found it very fascinating and how things are connected, because we don't know like how, like if you see the increment in the AI is causing pressure on the power. At the end, GPU has to support or process that much prompts that people are giving. So there are research going on, like NVIDIA is working on the GPU, because the GPU has to handle, say imagine GPU is not able to handle, then it cannot process. So first of all, GPU should exist so that it can meet the requirement of the users, and on top of that, the PoL has to exist to supply the power that the GPU is demanding. So research is going on PoL. At the same time, IBC should also is a part of this, right? So this also has to be part of that. Yeah, so this overall everything is connected. Now if the requirement is increasing, then the data centers has to increase. So people are also working on data centers, how to build more data centers, and again, who will give the power to data center? That is also part. And then it also needs cooling. So there are many issues related to this, and again, researchers are going in different types of directions, and this is just one direction. Yeah. So one, I think probably this is the reason when this Ghibli trend was going on, everyone was asking for a picture, right? So now who does this? The GPU, and I think Sam Altman also has announced it that the GPUs are melting because of too many prompts. So then they have reduced the prompt intake. So ChatGPT, they have reduced the intake of the prompt because the GPU was not able to handle so much image processing from crores of people. So they have temporarily reduced the prompt. So it was not editing the picture, just to reduce the traffic. If everyone all over the world starts giving high processing prompts, then it is limited by the GPU as well as the hardware that we have. So that's why they had to do from their side so that their data centers will not be loaded. But in the future, they are trying to improve these aspects. Again, this may not be the part of ChatGPT itself. ChatGPT will try to uh, optimize the resources, but NVIDIA or AMD, who are making these GPUs, they'll try to incorporate those GPUs which will run more number of prompts or more instructions per second. So everything is becoming more power hungry. So it opens doors to multiple things. So the mobile phones or the laptops now have different AI processor, not the main processor, but a different processor which can run more instructions or like whatever. So neural processing unit, or they have again separate hardware to run these AI prompts. So this is just an overview because I found it fascinating. I thought I can share it to you since this topic has come in this week. Is that clear?
Yes, sir. Yes, sir.
Yeah, yeah.
Yes,
So
sir.
that's all for this week. If you have any queries, you can ask. Else we can wind this session.
So, yes, special thanks, sir. You have changed the timing to 7 o'clock.
Yeah,
Really,
yeah,
it
yeah.
helps me a lot. Also,
Yeah.
sir, when you are giving the feedback, you
Yes.
have the ratings 1 to 5, which is very good, which is slow. That I don't know. So I didn't give the feedback so far.
Okay. Since I have not opened, I think 5 is the best. If anyone in the students have filled the feedback, probably they can mention. Usually they'll mention
Madam,
there. I'm not sure. 5 may be the best.
Vijay Lakshmi ma'am, have you given it, ma'am?
Sorry, ma'am, I didn't do it yet.
Okay, in the feedback it was simply 1 to 5, but which is good, I don't know. That's why I didn't give in the past few weeks. Shall I make 5 as the best, sir?
I think so. If anyone in the group, if they have done, kindly help her. I don't know. I have not checked. So
Since we
let me.
shouldn't give it in the wrong way, no? So I didn't
Yeah,
give
yeah, I
it.
get it. Or you can send an email to them. They'll help you.
Okay, sir. Okay.
Okay.
Sure. Thanks a lot, sir. The
Yeah,
session
yeah,
was really informative.
yeah. Thank you, thank you.
Thank you, sir.
Yeah, yeah. I think Purva has mentioned 5 is the best. Yeah, so 5 is the best.
Okay.
Okay. Okay, then I wish you all the best for your assignment 3. Again, we'll meet next upcoming Monday
Next
with
week.
week 4. Yeah.
Okay, thank you.
Okay.
Thank you.
Purva
Okay.
says thank
Thanks
you.
a lot.
Thank you, everyone. Good night.